Okay, so we will continue on with 9.2 and we will finish it up. So we are ready to do example number 6, and that is the indeterminate form where you get something that looks like this. So example number 6. If you look at example number 6, it says a limit as x goes to infinity, x times sine 1 over x. Okay. So the trick here is to realize that we do not know this, but we know something that looks similar to this, or somewhat similar to this. When we were first starting out in our page 60, we learned about this, and we said that this guy, because the graph looks like this would be equal to 1 right here, where it doesn't exist. This is an open dot because obviously the function y is equal to sine x over x. X cannot be 0, but the actual limit is going to be 1. So we do know this. We don't know this. So the trick here is to say that if I say h is equal to 1 over x, what happens? What do I get? So this guy is going to be equal to x goes to infinity. As x goes to infinity, h approaches 0. And this becomes 1 over h. And the sine of h goes in here. And this obviously becomes, when h goes to 0, h over sine h, which is equal to 1. Okay? So that's how that one works. And if you look at b, it's exactly the same, except for x is approaching from negative infinity. And it doesn't really matter because h goes to 0, approaches 0 from 2 different points. But it doesn't really matter which side you approach it from, you still get 1. So b and a and b will both be equal to 1. Okay? Example number 7. Example number 7, we're going to go ahead and they are asking us to do, as x approaches 1, so as x approaches 1, we're going to do the natural log of x, 1 over natural log of x minus 1, minus 1 over x minus 1, x minus 1, x minus 1. So the first thing to do is we're going to combine the denominator. As x approaches 1, I get natural log of x, x minus 1. I get x minus 1 minus natural log of x. So what happens when I put x equals 0 in here? When I have x equals 1 in here? When I put x equals 1, I get this is 0, so this bottom part is both 0. I get 1 minus natural log of 1, 0, and this is 0. Also, I get 0 over 0, so this is a form where we can use the L'Hopital rule here. So let's go ahead and take the derivative of the top. Limit as x approaches 1, I get 1. This goes away, minus 1 over x. In the bottom, I'm going to have to do the product rule. So I keep this guy, take the derivative of that, plus take the derivative of this, which is 1, times, just keep that, natural log of x. Okay? When x approaches 1, what do I get? I get 1 minus 1. So that's 0 on top. This is 0. And this guy is 0 also. I get 0 over 0. So this is the strong form because I have to do it twice. I did it once here. I'm going to do it again. So I'm going to take the derivative of top and bottom. So I get limit as x approaches 1. I get 1 over x squared on top. On the bottom, what do I get? So I'm going to go ahead and change this to 1 minus 1 over x plus natural log of x, right? I can do that because this is 1 over x, and this is 1, this is 1, and this is negative 1 over x. So I take the derivative, I get this guy, which is 1 over x squared again, and plus x over 1. Multiply top and bottom by x squared. Limit as x approaches 1, I get 1. 1 plus x. X is going to 1. 1 over 2. Okay, and that was example number 7, actually. That was 7. Okay. Now let's move on to example number 8. Example number 8 is something that's pretty complicated. And it's complicated in the sense that if you look at what they asked us to do, it says find the limit of x goes to infinity 1 plus 1 over x over x. Okay? So what's the problem here? What's different than all the things that we've seen before? This one actually has an x in the exponent. So when you're doing limits, if you see an x up here, that's a clue that you are to try to, you want to get rid of this somehow, right? Because you can't take the derivative of this, okay? What happened last time when we couldn't take the derivative of this when we had something up here? We ended up taking the natural log of that. So if you say that f of x is equal to 1 plus 1 over x divided over x, if I take the natural log of f of x, I'm going to get what? X is going to come down 1 plus 1 over x, correct? Then what else am I doing? So, x times natural log of 1 times x. If I go ahead and divide this guy down here, I'm going to end up with natural log 1 plus 1 over x over 1 over x if I wanted to. I can put it this way, right? Okay. So I'm not going to find this directly. What I'm going to try to find is I'm going to try to find the limit of the natural log of f of x. Okay, if I take the natural log of f of x, if I take the derivative of that, I can go like this. X goes to infinity. Natural log of 1 plus 1 over x, 1 over x. Okay, so what do I get here? If I get x goes to infinity, this goes to 0. This guy goes to 0, so natural log of 1, so I get 0. So it's 0 over 0, correct? So I can take the L'Hopital's rule now, right? I'm going to get limit as x goes to infinity. If I take the derivative of this, I get 1 over x squared. I take the derivative of this, what do I get? I get 1 over 1 plus 1 over x. Then I have to do the chain rule. So what do? I have to take the chain rule, I take the derivative of this guy. And that's what ends up happening, right? So what happens here, these guys cancel out. I get natural log, this goes to, as x goes to infinity, 1 plus 1 over x. This guy goes to 0, I end up with 1 over 1. So I'm not done here, but I actually have found a limit of something. I found the limit of the natural log of f of x. So I know that the limit of natural log is going to go here. So if the natural log of this function is going to go to 1, I can say that the function itself is going to go like that. So the function itself, the limit is going to go to e. As a matter of fact, many of a textbook use that as a definition for the number e. Okay? Pretty tricky, because instead of finding directly the limit of f of x, I found the limit of the natural log of f of x, and then found the limit of f of x. Okay? So that was example number 8, I guess. That was example number 8. Let's work on example number 9 now. Okay, example number 9. Example number 9. We have determine, okay, so we're trying to find as limit as x approaches 0 from the positive side, that guy. Okay? Alright? So, again, x is in the exponent, and the exponent includes an x, so I'm going to say this is f of x, and I'm not going to find directly the limit of f of x. I'm going to find the limit of the natural log of f of x. And if I do that, I get something that looks like that. Okay? So the limit of, as x approaches 0 to the positive side, the natural log of f of x is going to be equal to the same as x approaches 0 positive, x natural log of x. Okay? Okay, so also I can go ahead and say, again, like I did before, I can go like that and say that. So let's go ahead and call like that. X goes to 0, I get infinity here, right? X goes to 0 here, what do I get? I get negative infinity here. So I'm going to get a form that looks like this, and looks like this is infinity also. Okay? Right. So I'm going to do the L'Hopital rule here. Limit as x approaches x from the positive side. I take the derivative of this. I take the derivative of this. This is what I get. If I multiply top and bottom by x squared, I get limit x approaches to the positive. I get negative x over 1. So in other words, I'm going to get 0. Okay? So, since the natural log of the function limit goes to 0, so that means that it's a natural log of f of x goes to 0, the f of x, when I go to take the limit, is going to be that, which is 1. So it approaches 1. Okay? And on the very last one, example 10, it says x goes to infinity, x over, so example number 10 says as x goes to infinity, and they want us to find out x to the 1 over x. So again, so it's going to be 1 over x. I'm going to take the natural log of both sides. I get that, so I am going to end up with something that looks like that. Okay, so we are now going to infinity. Natural log of that. So let's go ahead and evaluate that and see where we stand. Okay, what do I get here? As x goes to infinity, the top one goes to infinity. As this one goes to infinity, obviously it's going to go to infinity. So we get infinity over infinity, so we can use the L'Hopital rule here. Let's go ahead and take the derivative of the top and the bottom. We're going to infinity here. So I take the derivative of this, I get 1 over x. I take the derivative of this, I get negative 1 over x squared. Okay? So what do we get here? Oh, this is not x, right? This is just 1. What am I doing here? This is 1. 1 right here. So I'm going to end up getting limit as x goes to infinity. 1 over x, as x goes to infinity, this guy becomes 0. So again, I have the natural log of f of x is going to go to 0. So the f of x itself is going to go to that, which is 1. Okay? And with that, we will be done with 9.2.